Is what you're seeing right now real? The screen in front of you, the room around you, even your own hands, how can you be certain any of it truly exists as you perceive it? This isn't some abstract philosophical exercise. It's a question that cuts to the very core of our existence, one that has haunted brilliant minds for centuries. We go about our days trusting our senses, rarely stopping to wonder whether the world we experience is just a convincing illusion, a carefully constructed reality filtered through our brains. Yet what if everything you've ever known, every sensation, memory, and moment is merely a shadow of something far stranger and more magnificent? Today, we're going to explore that profound mystery together. We'll venture into the bewildering world of quantum physics, where particles exist in multiple states at once and reality itself seems to shift under observation. We'll navigate the intricate pathways of neuroscience to understand how your brain constructs the world you believe is real. And we'll wander through the deep questions posed by philosophy, grappling with ideas that challenge our most basic assumptions about consciousness and existence. This journey won't just reshape how you see the universe, it might just redefine how you see yourself. You're about to embark on an adventure that spans from the smallest building blocks of matter to the vast, mysterious expanse of the cosmos. Along the way, we'll uncover insights that have puzzled scientists, thinkers, and dreamers for generations. There's a certain magic in questioning the nature of reality. It invites us to look beyond the surface and discover that the truth is often more extraordinary than anything we could have imagined. So settle in, open your mind, and get ready to explore one of the most captivating questions ever asked. What is reality, really? Long before scientists peered through telescopes or studied subatomic particles, the ancient Greeks were already wrestling with the nature of reality, asking questions that still echo in our minds today. To truly appreciate how far we've come, we have to go back to where it all began, to the foundational ideas that first challenged humanity to look beyond the obvious. Two of the most influential thinkers, Plato and Aristotle, approached the mystery of reality from dramatically different angles, and their debate continues to shape how we interpret the world around us. Plato, a student of Socrates, introduced one of the most powerful thought experiments in history, the allegory of the cave. He asked us to envision a group of people who have lived their entire lives chained inside a dark cave facing a blank wall. Behind them, a fire burns, and between the fire and the prisoners, objects are passed, casting shadows on the wall in front of them. For these prisoners, those shadows are reality. They name them, discuss them, and believe them to be the fullest extent of what exists. They have no reason to suspect there's anything more. Now, what if one prisoner were freed? He would turn around, see the fire and the objects, and be utterly bewildered. His eyes would ache from the light, and the new images would seem less real than the familiar shadows. If he were then dragged out of the cave entirely into the blinding sunlight, he would be overwhelmed, gradually adjusting to see the world as it truly is: trees, clouds, the sun itself. He would understand that everything he once believed was mere illusion, and if he returned to the cave to tell the others, they wouldn't believe him. They'd think the journey had ruined his sight and his mind. They might even become hostile, preferring the comfort of their familiar shadows over the unsettling truth. This story is far more than an ancient parable. It's a profound metaphor for the human condition. Plato was arguing that the world we perceive with our senses, the world of physical objects, sounds, and sights, is merely a shadow, a flawed copy of a higher, truer reality. He called this truer reality the realm of forms, perfect, eternal, and unchanging ideals of which everything we see is just an imperfect imitation. The form of a circle, for instance, is a perfect circle, something that can never truly exist in our physical world of rough sketches and wobbly wheels. For Plato, true knowledge came from using reason to grasp these eternal forms, to escape the cave of sensory deception. His student Aristotle, however, took a dramatically different view. While he respected his teacher, Aristotle was far more grounded. He rejected the idea of a separate, invisible world of perfect forms. For him, reality was right here, in the substance of the world we can touch, study, and categorize. Aristotle believed that every object in the physical world has two essential parts: its matter, what it's made of, and its form, the structure or essence that makes it what it is. The form of a statue isn't in some other dimension. It's right there in the marble shaped by the sculptor. He urged us to trust our senses, to observe the natural world carefully and systematically, because truth could be found within the details of reality itself. Where Plato was the ultimate idealist, pointing beyond the physical, Aristotle was the empiricist, deeply invested in understanding the physical world on its own terms. This fundamental disagreement between a reality that transcends our senses versus a reality that is embedded within them set the stage for centuries of philosophical and scientific inquiry. It's a tension we still haven't resolved. Are we, like Plato's prisoners, mistaking shadows for substance, or can we, like Aristotle, trust that by closely examining the world we can uncover its true nature? These ancient questions don't just belong in textbooks, they are the very bedrock upon which our modern search for truth is built, challenging us to constantly question what we think we know. While the Greeks laid a foundation of logic and observation that would profoundly influence the Western world, on the other side of the globe, ancient Indian and Chinese sages were cultivating a radically different understanding of existence. Their exploration wasn't focused on defining an external, objective reality, but on penetrating the inner nature of consciousness itself. To journey east is to step into a worldview where the solid, tangible world we take for granted begins to shimmer and dissolve into something far more fluid and mysterious. In Hindu philosophy, particularly in the Advaita Vedanta school, we encounter the profound concept of Maya. This is often translated as illusion, but that simple word can be deeply misleading. Maya doesn't suggest that the world is a simple trick or a hallucination. Instead, it describes the world as a grand, divine projection, a kind of cosmic magic show performed by Brahman, the ultimate formless reality. Think of it like a masterful film. The images on the screen appear vividly real. You feel joy, fear, and suspense for the characters. Yet, the entire experience is generated from a single light source projecting through a reel of film. Maya is that projection. The world of separate objects, individuals, and events is the captivating movie, while Brahman is the singular, unchanging light source. The goal of spiritual practice is to see through the projection, to realize that the apparent multiplicity of the world is a temporary appearance superimposed on a unified whole. The seeker aims to attain moksha, liberation, which is the profound realization that one's true self, the Atman, is not separate from Brahman at all. It is the recognition that you are not a character in the movie, but you are the light itself. Buddhism, which grew from the soil of Hindu thought, takes this idea of illusion even further. The Buddha's core insight was into the nature of anicca, or impermanence. He observed that nothing in the phenomenal world possesses a fixed, independent identity. Everything is in a constant state of flux, dependent on countless causes and conditions. This leads to the doctrine of anatta, often translated as no self. The Buddha taught that what we consider to be our self, a permanent, unchanging soul or ego, is merely a temporary construct, a flowing stream of 5 aggregates: form, sensation, perception, mental formations, and consciousness. There is no solid captain steering the ship, only the ship itself, made of countless shifting parts. Therefore, the reality we cling to is not just illusory because it's a projection, but because it is fundamentally empty of inherent, independent existence. This is sunyata, or emptiness. It's not a void of nothingness, but a fullness of potentiality, free from our limited concepts and labels. Suffering arises from our attachment to these illusions, from desperately trying to hold onto things that are by nature fleeting and insubstantial. Traveling to ancient China, Taoism offers a more poetic and naturalistic perspective. The Tao, which translates to the way, is the undefinable underlying principle of the universe. It is the spontaneous, effortless process of nature from which all things emerge and to which they all return. Taoist sages observed that the human mind, with its constant discrimination and desire to label things as good or bad, high or low, real or unreal, creates a fractured and conflicted experience of the world. This mental categorization is the source of our alienation from true reality. The famous Taoist parable of the farmer whose fortunes constantly shift illustrates this perfectly. What seems like misfortune one day becomes a blessing the next, revealing the folly of our rigid judgments. True wisdom, according to texts like the Tao Te Ching, lies in Wu Wei, or non-action, not laziness, but a harmonious alignment with the natural flow of the Tao, like a leaf floating effortlessly on a river's current. From this perspective, reality isn't a problem to be solved by the intellect, but a dance to be experienced with intuitive, effortless participation. What unites these Eastern views is a shared suspicion of the naive realism that often characterizes Western thought. They uniformly suggest that the everyday world of separate objects is a conventional reality, a useful but ultimately provisional map, not the territory itself. The ultimate goal is not to analyze the map more precisely, but to wake up from the dream of being a separate map reader and to realize one's fundamental identity with the source of all that is. This stands in stark contrast to the Aristotelian tradition that sought to categorize and understand the physical world on its own terms. Where the West often moved outward to conquer and understand nature, the East turned inward to conquer the mind and realize its unity with nature. These are not conflicting truths, but rather complementary dimensions of a mystery far too vast for any single perspective to contain completely. For all their profound wisdom, the ancient worldviews of both East and West were ultimately built on observation and introspection. It would take a radical shift in thinking, a true revolution, to forge a new toolkit for probing reality, one based not on pure reason or spiritual insight, but on measurement, experiment, and the unshakable language of mathematics. This seismic shift began in the 17th century, a period of upheaval that would shatter the medieval cosmos and replace it with a breathtaking new vision. A universe that ran with the precise, predictable regularity of a clock. At the heart of this revolution was a pivotal change in our relationship with nature. Before this era, to understand the world was to seek its ultimate purpose, its why. The scientific revolutionaries, however, asked a different, far more powerful question: how? How do objects move? How do the planets travel in their orbits? This shift from purpose to mechanism opened the door to a new kind of answer, one written in the universal language of mathematics. The Italian polymath Galileo Galilei stands as one of the most important architects of this new perspective. He was arguably the first to truly fuse mathematics with physical experiment. Before Galileo, much of science was still deeply influenced by Aristotle, who claimed, for instance, that heavier objects fall faster than lighter ones. Galileo, the story goes, didn't just argue, he tested. He is said to have dropped spheres of different masses from the Leaning Tower of Pisa, demonstrating that they hit the ground at nearly the same time, air resistance aside. But his greater genius was in his use of the inclined plane. By rolling balls down a gently sloping ramp, he could slow the action of gravity down enough to measure it meticulously. Through this painstaking work, he didn't just make observations, he discovered mathematical laws describing motion. He found that the distance a falling object travels is proportional to the square of the time elapsed. This was a monumental leap. Galileo showed that the book of nature, as he famously stated, is written in the language of mathematics. He wasn't just studying reality, he was decoding it. While Galileo was looking through his telescope and charting the motions of Jupiter's moons, the French philosopher René Descartes was providing the crucial philosophical underpinning for this new mechanistic world. Troubled by the potential for doubt in everything he knew, Descartes sought an indubitable foundation for knowledge. His famous conclusion, cogito ergo sum, I think, therefore I am, established the thinking self, the mind, as the only certain reality. From this starting point, he made a fateful deduction. If the mind is the realm of thought, then the entire external world, including our own bodies, must belong to a separate category of substance, which he called res extensa, or extended stuff. This was the world of matter, which could be understood purely in terms of its geometric properties, size, shape, and motion. In one sweeping philosophical move, Descartes had divided the universe in two: the inner world of the mind and the outer, mechanical world of matter. This Cartesian dualism provided a clean intellectual space for scientists to study the physical world as a vast, complex machine, without having to constantly worry about its relationship to the soul or consciousness. The physical universe was now a machine, and its workings could be understood through reason and mathematics. It was the English genius Isaac Newton who assembled these pieces into a breathtakingly complete and powerful system. In his monumental work, the Principia Mathematica, Newton laid down a set of universal laws of motion and a law of universal gravitation that could explain everything from the fall of an apple to the orbit of the moon. His laws were stunning in their simplicity and breathtaking in their scope. Every action has an equal and opposite reaction. An object in motion stays in motion unless acted upon by a force. And every particle of matter in the universe attracts every other particle with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. With these few mathematical statements, the cosmos was unified. The same force that governed the mundane world ruled the heavens. The universe was no longer a mysterious realm of spiritual purpose. It was a grand, predictable, and intelligible clockwork mechanism. If you knew the position and velocity of every particle in the universe, Newton's laws implied, you could calculate its entire future and past. This was the ultimate expression of the clockwork universe, a vision of absolute determinism and order. For centuries, this Newtonian model dominated scientific thought. It was incredibly successful, enabling unparalleled technological progress and fostering a profound faith in human reason. The world felt knowable, predictable, and solid. Reality was not an illusion or a shadow. It was a magnificent machine operating according to fixed, intelligible rules. Yet, this very success sowed the seeds for its own challenge. The clockwork universe left little room for free will, consciousness, or the subjective quality of experience, all things that feel undeniably real to us. It created the very hard problem of consciousness that we still grapple with today. How does the mechanical motion of particles in the brain give rise to the rich inner world of thought and feeling? The scientific revolution gave us a powerful and accurate map of the physical territory, but in its rigorous focus on the how, it risked forgetting the why and the what it is like. The very questions that had launched the human quest to understand reality in the first place. For all its majestic power and precision, the clockwork universe described by Newton had one unshakable assumption at its core: that reality was local, deterministic, and independent of anyone watching it. A ball in flight followed a precise parabolic arc whether anyone was there to see it or not. The planets traced their elliptical orbits with silent, unwavering regularity, utterly oblivious to human observation. This was a universe of certainty, of predictable cause and effect. But just as this vision reached its peak, a series of discoveries in the early 20th century began to unravel it from the inside out, revealing a subatomic realm so bizarre that it would make the solid, familiar world seem like a comforting illusion. The first and most devastating blow to this classical certainty came from a seemingly simple experiment with a piece of card containing two parallel slits. Imagine a barrier with two narrow vertical cuts in it. Behind this barrier is a screen that lights up when particles hit it. Now, if you were to fire a stream of tiny pellets like BBs at the barrier, what would you expect to see on the screen behind it? Most would logically predict two bright bands directly behind the two slits where the pellets manage to pass through. This is exactly what happens when you use particles. But the world of the very small does not play by these rules. When scientists performed this experiment not with pellets, but with electrons, tiny fundamental particles of matter, something inexplicable occurred. They didn't produce two bands. Instead, they produced a series of multiple stripes, a pattern of light and dark bands known as an interference pattern. This is the kind of pattern that only waves make. Think of throwing two pebbles into a still pond. Ripples spread out from each impact point. Where the peaks of these two sets of waves meet, they create a higher peak, a point of constructive interference. Where a peak from one wave meets a trough from another, they cancel each other out, creating a point of destructive interference. The double-slit interference pattern is the signature of this wave behavior. So, the electron, a particle we think of as a tiny speck of matter, was somehow behaving as if it were a wave spread out in space, passing through both slits simultaneously and interfering with itself. This was baffling enough, but the true shock came when physicists decided to place a measuring device by one of the slits to see which opening each electron actually went through. The moment they did this, the act of observation itself changed the outcome. The elegant interference pattern vanished, and the screen simply showed two clumps, as if the electrons were now behaving like ordinary particles. It was as if the electron knew it was being watched and changed its behavior accordingly. This is the infamous quantum observer effect, and its implications are staggering. It suggests that at the fundamental level, particles do not have definite properties like a specific position until they are measured. Before measurement, they exist in a blurred state of all possible positions, a concept known as superposition. This isn't just a lack of knowledge on our part, it is a fundamental description of their reality. The electron is not here or there before we look. It is in a superposition of being here and there, a probability wave described by a mathematical equation. This wave is not a physical wave like water or sound. It is a wave of potentialities, a map of probabilities outlining where the particle might be found. The act of measurement, the interaction required to observe it, somehow forces this spread-out probability wave to collapse into a single, definite point. This introduces probability and chance into the very heart of reality, replacing Newton's deterministic clockwork with a universe that is fundamentally probabilistic. We cannot predict with certainty where an electron will appear. We can only calculate the probability of it appearing in any given location. As the physicist Max Born interpreted it, the wave function describes the probability of finding a particle in a particular place. This was so unsettling to Albert Einstein that he famously objected, declaring, "God does not play dice with the universe." He spent years attempting to find a deeper, deterministic theory hidden beneath the probabilities, but subsequent experiments have consistently upheld the bizarre quantum rules. The double-slit experiment forces us to confront a deeply strange conclusion. The solid, objective world of separate objects we perceive is an emergent property. At its foundation, reality is not a collection of distinct things but a flowing, interconnected web of potentialities. The simple act of looking, of asking a question of nature, seems to force a specific answer into existence. This doesn't mean consciousness literally creates reality in a simplistic way, but it does mean that the observer and the observed cannot be cleanly separated as Descartes believed. The universe at its most basic level is participatory. The properties of the quantum world remain undefined and smeared out in a cloud of possibility until an interaction, A measurement pins them down, irrevocably linking the nature of what is with the process of how we come to know it. This bizarre behavior, the wave-particle duality and the collapse of the probability wave, presents us with what is known as the measurement problem. If a particle exists in a fuzzy cloud of possibilities until we measure it, what exactly counts as a measurement? Where do we draw the line between the quantum weirdness of superposition and the definite classical world we experience every day? Is it the act of a conscious observer that causes the collapse, or is it simply any interaction with a larger system? The equations of quantum mechanics work flawlessly to predict outcomes, but they are silent on this profound question of interpretation. They give us the answers without explaining the test. Because of this, physicists and philosophers have been forced to step in, proposing a number of competing interpretations, each of which paints a radically different and mind-bending picture of the true nature of reality. The first, and for a long time the most prominent of these, is the Copenhagen interpretation, championed by figures like Niels Bohr and Werner Heisenberg. This view essentially argues that it is meaningless to talk about a particle's properties, like its position or momentum, before a measurement takes place. The particle isn't secretly somewhere, its state is genuinely indeterminate. The act of measurement itself, the interaction between the quantum system and a macroscopic measuring device, is what forces the wave function to collapse into a single reality. In this interpretation, the dividing line is pragmatic. The quantum realm operates by one set of rules, while the classical world of labs and scientists and cats operates by another. The Copenhagen interpretation is often summarized by the phrase, "shut up and calculate," prioritizing the practical use of the math over deep metaphysical questions about what is really happening. It accepts a certain inherent randomness and subjectivity at the foundation of the universe, a notion that many, including Einstein, found deeply unsatisfying. In direct opposition to this is the pilot wave theory, also known as the de Broglie-Bohm interpretation. This theory is a bold attempt to restore a measure of determinism and objectivity to the quantum world. It proposes that particles are indeed real, point-like objects with definite positions at all times. So, in the double-slit experiment, each electron goes through one slit or the other. But it is guided by a pilot wave, a real physical field that pervades all of space. This pilot wave is the solution to the Schrödinger equation, and it dictates the path the particle will take. The seemingly random outcomes we see are not due to fundamental indeterminacy, but to our ignorance of the exact initial conditions of the particle and its wave. If we knew every detail, we could predict the path perfectly. The eerie interference pattern emerges because the pilot wave passes through both slits, guiding the particles in such a way that they are attracted to the bright bands and repelled from the dark ones. This interpretation offers a comforting, concrete reality, but at a strange cost. The pilot wave is a non-local hidden variable, meaning it can influence particles instantaneously across vast distances, a feature that seems to violate the speed of light limit set by Einstein's relativity. Perhaps the most audacious and expansive solution to the measurement problem is the many worlds interpretation proposed by Hugh Everett III. Everett took the mathematical formalism of quantum mechanics with utter seriousness and asked a simple but profound question: what if the wave function never actually collapses? What if every single possible outcome encoded in that probability wave actually happens? In this view, when a measurement is made, the universe doesn't choose one possibility. Instead, it splits into multiple non-communicating branches. Every quantum event becomes a fork in the road for reality itself. In the famous thought experiment of Schrödinger's cat, the Copenhagen interpretation says the cat is both dead and alive until we look, which seems absurd. The many worlds interpretation says that in one branch of reality, the observer opens the box and finds a live cat, and in another, completely separate branch, an identical observer opens the box and finds a dead cat. Both outcomes are equally real, but they play out in parallel universes that are forever decoupled from one another. This means that right now, there are countless versions of you and me existing in branching histories, a multiverse of staggering proportions where every possibility is realized. It eliminates the need for a conscious observer or a mysterious collapse, but replaces it with an infinite, and to some, ontologically extravagant proliferation of realities. These are not the only contenders. Other interpretations like quantum Bayesianism, cubism, argue that the wave function is not a description of objective reality at all, but rather a tool that an agent uses to encode their own personal beliefs and probabilities about the outcomes of future experiments. In this view, quantum mechanics is not about the world itself, but about our interaction with it, a theory of information and subjective expectation. The collapse of the wave function is simply the agent updating their beliefs upon making a new observation, much like a gambler updating the odds after a new card is dealt. Each of these interpretations is a response to the same, impeccably accurate mathematics. They are all consistent with the experimental results, from the double-slit experiment to the most modern quantum test. And yet, they describe universes that are fundamentally, ontologically different. Do we live in a world that is fundamentally random and requires conscious observation to solidify? A world that is deterministic but guided by mysterious, faster-than-light waves? A world that is constantly branching into an infinity of parallel existences? Or a world where probability is purely a statement of personal belief? The measurement problem forces us to confront the unsettling fact that our most successful scientific theory of reality does not come with a single, obvious meaning. It presents us with a menu of metaphysical options, each more strange than the last, and leaves the choice of which world we believe we live in not to experiment but to us. Just as the quantum revolution was revealing a bizarre and probabilistic foundation to reality, a lone patent clerk in Switzerland was quietly dismantling the other pillar of Newton's clockwork universe, the very fabric of space and time itself. While Newton saw space as a static, unchanging stage and time as a universal ticker-tock that advanced at the same absolute rate for everyone, everywhere, Albert Einstein's theories of relativity would show that this common-sense view was profoundly mistaken. His insights revealed a universe where the stage itself is dynamic, warping and flexing, and where the rate of time's flow is anything but constant. Einstein first appended our understanding with his special theory of relativity in 1905. It was built on two deceptively simple principles. First, the laws of physics are the same for all observers moving at a constant speed. And second, the speed of light in a vacuum is always constant, regardless of the motion of its source or the observer. This second principle is the real mind bender. Imagine you're standing still and a friend races past you in a spaceship at 90% the speed of light. If your friend turns on a headlight, you might instinctively think that you would measure the light from that beam to be traveling at the speed of light plus the speed of the spaceship. But you would be wrong. Astonishingly, you will measure that light beam to be moving at exactly the same speed as if the spaceship were stationary, 299,792,458 meters per second. No matter how fast the source is moving, the speed of light is always the same. This single, stubborn fact forces us to abandon our deepest intuitions about space and time. To keep the speed of light constant for everyone, something else has to give. That something is time itself. Einstein realized that for your speeding friend, time literally slows down compared to your time. This is time dilation. If your friend's spaceship had a powerful clock visible from the outside, you would see it ticking slower than your own watch. And this isn't an illusion or a mechanical error. It is a fundamental property of time. Similarly, lengths in the direction of motion would appear to contract from your perspective. The faster an object moves through space, the more its progress through time slows. Space and time are not separate, rigid backdrops. They are woven together into a single, flexible fabric called space-time, and our experience of them is entirely dependent on our state of motion, our frame of reference. But Einstein wasn't finished. For 10 more years, he wrestled with a problem special relativity couldn't solve: gravity. Newton had described gravity as a mysterious, instantaneous force acting at a distance, but this idea made Einstein deeply uncomfortable. His general theory of relativity, published in 1915, offered a radically new and elegant explanation. He proposed that gravity is not a force at all. Instead, it is a consequence of the curvature of spacetime itself. Imagine spacetime as a taut, flexible rubber sheet. Place a heavy bowling ball in the center, and it creates a deep dimple. Now roll a marble across the sheet. It won't travel in a straight line. It will curve inward, orbiting the bowling ball as if pulled by a force. The marble is simply following the straightest possible path through the curved geometry of the sheet. In our universe, the bowling ball is a star or a planet, and the marble is a spacecraft or a beam of light. The Earth orbits the Sun not because it is being pulled by an invisible string of force, but because it is following a geodesic, the equivalent of a straight line, in the curved spacetime around the Sun. This curvature explains phenomena that Newtonian gravity could not. For instance, light, which has no mass, should not be affected by gravity in Newton's model. But Einstein predicted that light would bend as it travels through warped spacetime. This was spectacularly confirmed during a solar eclipse in 1919, when starlight passing near the Sun was observed to be deflected from its path. General relativity also predicts the existence of gravitational waves, ripples in the fabric of spacetime itself, sent out by cataclysmic events like colliding black holes, which were directly detected a century later. Perhaps most strikingly, general relativity dictates that the stronger the gravity, the slower time flows. A clock at sea level, closer to Earth's mass, ticks imperceptibly slower than a clock on a mountaintop. GPS satellites orbiting high above Earth have to constantly correct for this effect. If their internal clocks weren't adjusted for both special and general relativity, the navigation system we rely on would be inaccurate by several miles within a single day. Together, relativity and quantum mechanics form the twin pillars of modern physics, and yet they present us with a fundamental schism. Relativity paints a breathtaking picture of a smooth, continuous, and deterministic cosmic landscape, where everything from the path of a planet to the flow of time is governed by the elegant geometry of curved spacetime. Quantum mechanics, by contrast, reveals a jittery, probabilistic, and granular subatomic world where certainty is replaced by probability and particles flicker in and out of existence. For decades, physicists have struggled to reconcile these two magnificent but seemingly incompatible theories into a single, unified description of reality, a so-called theory of everything. This quest forces us to ask an even deeper question. If our most fundamental theories of the universe are in conflict, what does that tell us about the nature of reality itself? Is the smooth spacetime of relativity merely an emergent property, an average of a deeper quantum reality we have yet to comprehend? This profound conflict between our two most successful theories of physics, the smooth, geometric cosmos of general relativity and the fuzzy, probabilistic quantum world, has driven scientists to propose some of the most radical ideas in the history of human thought. Among these, one of the most astonishing and mind-expanding is the holographic principle. This concept suggests a possibility so strange it seems ripped from the pages of science fiction, that everything we perceive in our three-dimensional universe, including you and me, might actually be a projection, a kind of elaborate illusion encoded on a distant two-dimensional surface. The story of this incredible idea begins not with the whole universe, but with one of its most enigmatic objects, the black hole. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole must have entropy, Entropy is a measure of disorder or randomness in a system, and it is also deeply connected to information. What Wittgenstein realized was that when matter falls into a black hole, it disappears from our universe, seemingly violating a fundamental law of physics. That information cannot be destroyed. His insight was that the information about that swallowed matter wasn't lost. It had to be encoded on the black hole's surface, its event horizon. The event horizon is the point of no return, the two-dimensional boundary around a black hole from which not even light can escape. Wittgenstein suggested that the entropy of a black hole, which is a measure of its information content, is proportional to the area of its event horizon, not its volume. This was a revolutionary departure from everything we knew. In our everyday world, the entropy of a system, like the amount of information you can store in a box, depends on its volume. A bigger box can hold more stuff and therefore more information. But for a black hole, the information capacity is linked to its surface area. It's as if all the data needed to describe the three-dimensional interior of the black hole is painted or encoded on its two-dimensional surface. This idea was later placed on a firm mathematical footing by Stephen Hawking through his work on Hawking radiation, which confirmed that black holes do indeed have temperature and entropy. The brilliant Dutch physicist Gerard T. Hooft took this concept and ran with it, proposing a breathtaking extrapolation. If the information for everything inside a black hole is stored on its surface, could the same be true for the entire universe? His colleague Leonard Susskind developed this idea further, coining the term holographic principle. The principle posits that our entire three-dimensional reality, with its galaxies, stars, planets, and people, might be a holographic projection from a two-dimensional surface at the very boundary of the observable universe. In this view, the universe we experience is like a magnificent three-dimensional movie being shown to us, but the actual data for the movie, the complete source code of reality, resides on a flat, two-dimensional screen trillions of light years away. This isn't a literal hologram like the kind on a credit card. It's a profound statement about the nature of information and dimensionality. The key idea is that the fundamental bits of reality are not scattered throughout the volume of space, but are instead all located on its boundary. What we perceive as a third dimension of depth is actually emergent, generated by the complex processing of this two-dimensional information. Think of it like watching a television show. The images appear to have depth and movement, characters walking through rooms and landscapes, but all that information is encoded on the flat, two-dimensional surface of the screen. The holographic principle suggests our universe operates in a similar way. The three dimensions we move through are a compelling and convincing display, while the true workings of reality are happening on a distant, lower-dimensional surface. String theory, a leading candidate for a theory of quantum gravity, provides a tantalizing mathematical framework that supports this idea. In certain simplified models of a universe governed by string theory, physicists have been able to show that a gravitational theory operating in a volume of space is completely equivalent to a quantum field theory operating on its lower dimensional boundary. This is known as the AD/S/CFT correspondence, and it is a concrete mathematical realization of the holographic principle. It demonstrates that there is no fundamental difference between the two descriptions. They are two equivalent ways of describing the same underlying reality. One description has gravity and three spatial dimensions. The other has no gravity and two spatial dimensions, yet they are mysteriously, perfectly dual to one another. If the holographic principle is correct, it would have staggering implications for our understanding of reality. It would mean that the universe is fundamentally pixelated, not smooth. There would be a finite, maximum amount of information that can be contained in any given region of space, determined by its surface area and not its volume. This introduces a fundamental limit to reality, much like how a digital image becomes blurry when you zoom in too far because you eventually see the individual pixels. At an incredibly tiny scale, the famous Planck scale, space-time itself might cease to be smooth and continuous and instead reveal a granular, information-based structure. We are unable to perceive this pixelation because the pixels of space-time are unimaginably small, but it would mean that the continuous, flowing universe described by general relativity is an approximation, an emergent property of a deeper, two-dimensional reality. This principle offers a potential path to resolving the conflict between general relativity and quantum mechanics. Gravity and the three-dimensional space-time it warps may not be fundamental forces or stages, but may themselves emerge from a more basic, non-gravitational quantum reality that exists on a distant two-dimensional surface. The holographic universe is a profound and humbling concept. It suggests that the richness of our experience, the feeling of the wind on your face, the depth of a starry night, the vast three-dimensional expanse of the cosmos is an incredibly immersive and complex illusion. We are not just in the universe in all its apparent solidity and depth is in a very real sense within something else entirely. But if the universe is, in some sense, a projection or an information-based construct, this leads us to one of the most provocative and widely discussed ideas of our time, the simulation hypothesis. This concept suggests that if reality is fundamentally computational, then it is not only possible but perhaps even probable that our entire existence is a sophisticated simulation, not unlike an incredibly advanced video game being run on some form of cosmic computer. This isn't just science fiction fodder. It's a serious argument that has been advanced by philosophers, supported by some interpretations of quantum mechanics, and even entertained by prominent technologists. The modern formulation of this idea is most famously associated with the philosopher Nick Bostrom of Oxford University. In 2003, he published a paper titled, "Are You Living in a Computer Simulation?", in which he laid out a simple but powerful trilemma, a set of three possibilities, one of which he argues must almost certainly be true. The argument rests on a few reasonable assumptions. First, that a sufficiently advanced civilization would possess enormous computing power, and second, that such a civilization might have a desire to run detailed simulations of its ancestors for research, entertainment, or historical preservation. Bostrom's three propositions are as follows. 1. Almost every civilization at our level of development goes extinct before becoming technologically mature enough to create such simulations. 2. Almost every technologically mature civilization loses interest in creating ancestor simulations. Or 3. We are almost certainly living in a computer simulation right now. The logic is statistical. If the first two propositions are false, if a significant number of civilizations do survive and do choose to run these simulations, then the number of simulated minds could be astronomically larger than the number of biological original minds. There could be billions of simulations, each containing billions of conscious beings. If that's the case, the odds that you and I are among the tiny fraction of original biological beings are vanishingly small. It is far more likely that we are one of the simulated ones. This argument doesn't prove we are in a simulation, but it forces us to confront the statistical probability that it might be true. Intriguingly, some aspects of modern physics seem to offer curious clues that could be interpreted as evidence for a simulated reality. Take the phenomenon of wave function collapse in quantum mechanics, which we just explored. The idea that particles exist in a blurry state of probability until they are observed or measured has often been likened to a video game's rendering engine. In a complex virtual world, processing power is limited. To save resources, the game doesn't render every detail of the entire world at once. It only generates the graphics and physics for the parts of the world that the player is currently looking at. The rest remains in a low-resolution, unprocessed state. Could the quantum observer effect be the universe's way of optimizing its computational load, only a rendering definite reality when someone is looking? Furthermore, the discovery that the universe appears to have a fundamental resolution limit supports this analogy. Just as a digital image becomes pixelated when you zoom in too far, space-time itself might be granular at the smallest possible scale, the Planck length. You cannot measure anything smaller than this. It is the universe's pixel size. The finite speed of light could be seen as the processing speed limit of the cosmic computer, setting a maximum frame rate for reality. Even the mathematical nature of the universe, which we've seen from Galileo to quantum physics, is a strong hint. We live in a cosmos that appears to be written in the language of mathematics, a language perfectly suited for computation. If reality is a simulation, then mathematics is its source code. Of course, the simulation hypothesis is not without its fierce critics and logical puzzles. Some argue that it is an unfalsifiable proposition. There is no conceivable experiment we could perform from within the simulation to definitively prove we are in one, as any evidence we find could itself be part of the simulation. This moves it into the realm of metaphysics rather than science. Others point out the problem of infinite regression. If we are a simulation created by an advanced civilization, who is to say that civilization isn't itself a simulation created by an even more advanced one? This leads to an endless chain of simulators with no original, base reality in sight. Perhaps the most significant challenge is the question of consciousness. Even if you could simulate every physical particle and force in a human brain with perfect accuracy, would that simulated brain actually experience qualia, the subjective feeling of being, the redness of red, the pain of a stubbed toe? This is the hard problem of consciousness, and if you believe that consciousness is a non-physical emergent property or something fundamentally non-computable, then even a perfect physical simulation could never truly create a conscious being that experiences reality. It would merely be a philosophical zombie going through the motions without any inner life. In this view, the very fact that we experience the world so vividly is the strongest argument against the simulation idea. Yet the hypothesis persists, capturing our imagination because it resonates with our increasingly digital lives and forces a radical rethink of our place in the cosmos. It combines ancient philosophical questions about illusion with cutting-edge science and technology, creating a narrative that is as unsettling as it is fascinating. Whether we are living in a simulation or not, the very act of considering it changes our perspective. It invites a certain humility, suggesting that our reality, for all its visceral intensity, might be just one layer of a far grander and more mysterious existence. It challenges us to look for the seams in the fabric of the universe, to question the nature of our own consciousness, and to wonder not just what reality is, but who or what might be wondering about us. If the universe around us has such a strange and uncertain foundation, then how do we, as human beings, manage to navigate it with such apparent ease? The answer lies not in the outer cosmos, but within the 3-pound universe inside our own skulls. Our brain is not a passive camera simply recording objective reality. Instead, it is an active, relentless prediction engine, constructing our experience of the world from the ground up. Every sight, sound, and sensation you believe you are perceiving is actually a best-guess simulation, a controlled hallucination generated by your neural circuitry. This construction process begins with our senses, but they are far from perfect windows to the world. Our eyes, for instance, don't see everything. They have a blind spot where the optic nerve connects to the retina, a hole in our visual field that our brain seamlessly fills in with surrounding patterns. The raw data coming from our retinas is also upside down, two-dimensional, and blurry at the edges. It is your visual cortex that must work tirelessly to rotate it, add depth, and sharpen the details, stitching together a coherent image from fragmented clues. And we are only sensitive to a tiny sliver of the electromagnetic spectrum, seeing what we call visible light, while completely missing the vast infrared, ultraviolet, and radio waves that fill the same space. Our reality is already filtered, limited to what our biological hardware can detect. This limited and ambiguous sensory data is then sent to the brain for interpretation, and this is where the real magic happens. The brain doesn't have the luxury of waiting to figure out what something is. Survival depends on speed. To achieve this, it uses a powerful strategy called predictive coding. Instead of processing every detail from scratch, your brain constantly generates models of the world based on your past experiences, beliefs, and expectations. It then uses incoming sensory information merely to check and correct its predictions. In essence, your brain is always asking, based on what I know, what is this most likely to be? You're not hearing sound waves, you're experiencing your brain's prediction of the source of those waves, which is why you can understand a friend's mumbled words in a noisy room. Your brain predicts what they were likely to say. This predictive model explains why two people can witness the exact same event and walk away with entirely different stories. Their brains, shaped by unique lifetimes of experiences, are starting with different sets of prior beliefs and expectations. A classic example is the rivalry between sports fans. When a referee makes a close call, fans of one team will almost universally see it as a fair decision, their brains predicting a justified outcome based on their loyalty. Fans of the opposing team with a different set of priors will predict a bad call and literally perceive the same event as an injustice. Their brains aren't lying, they are just constructing different realities from the same sensory input. We can see this neural magic at work in countless optical and auditory illusions. The famous checker shadow illusion by Edward Adelson shows two squares labeled A and B. To our eyes, square A looks a dark brown and square B looks a much lighter cream color. Astonishingly, they are exactly the same shade of gray. Your brain, seeing that B is in a shadow, predicts that an object in shadow would reflect less light. To maintain a consistent perception of the checkerboard's colors, it overrides the actual sensory data and adjusts the perceived color of square B, making it appear lighter than it truly is. Your perception of color is not absolute, it is a relational calculation made by your brain. Similarly, the rubber hand illusion demonstrates how malleable our sense of self is. If a person hides their real hand and instead looks at a realistic rubber hand while both the rubber hand and their real hand are stroked simultaneously with a brush, their brain will soon predict that the rubber hand is their own. This prediction is so strong that they will flinch if the rubber hand is suddenly threatened with a hammer. A powerful testament to how what we feel as our body is also a constructed perception. This means the reality you experience is a personalized interpretation, a unique blend of the external world and the internal world of your mind. It is a useful, functional interface designed for survival, not a perfect mirror of objective truth. Your brain's primary job is to keep you alive, not to show you the world as it actually is. It hides the blind spot in your vision, edits out the constant saccadic jerks of your eyes to create a stable visual scene, and even creates the feeling of a continuous self from the myriad of shifting thoughts and sensations. Understanding this doesn't diminish the wonder of our experience, it deepens it. It reveals that each of us is living in a subtly different world, a bespoke reality crafted by our own neural history. The world you see is, in a very real sense, a story told by your brain, a story that is compelling, coherent, and beautifully, profoundly your own. This incredible process of neural construction, where our brains build a tailored model of the world for us to inhabit, inevitably leads to one of the most profound and enduring mysteries in all of science and philosophy, the hard problem of consciousness. We can map neural pathways, understand predictive coding, and deconstruct sensory input, but none of this explains why any of this processing is accompanied by a subjective experience at all. Why do we have a rich inner life, a feeling of what it is like to be? This question, posed by philosopher David Chalmers, separates the so-called easy problems of consciousness, explaining how the brain integrates information or focuses attention, from the truly hard problem, why and how physical processes in the brain give rise to subjective qualitative experience, what philosophers call qualia. The sensation of the color red, the taste of chocolate, the ache of sadness, these are not just data points. They are experiences, and their existence seems to defy a purely material explanation. This challenge has forced thinkers to propose radical theories that venture far beyond conventional neuroscience. One of the oldest and most intriguing is panpsychism, the idea that consciousness is not a rare product of complex brains, but a fundamental and ubiquitous feature of the universe. In this view, just as matter has properties like mass and charge, it might also have a tiny bit of consciousness or proto-consciousness. A proton, an electron, or even a particle might possess an infinitesimal degree of inner experience. Panpsychism doesn't claim that an electron is sad or a rock is thoughtful. Rather, it suggests that the most basic building blocks of reality have an inner aspect, however simple. The complex consciousness we experience as humans, then, is not created from nothing by our brains, but is instead orchestrated or combined from these fundamental conscious units. Our brain might be less a generator of consciousness and more an aggregator or complexifier of it, a receiver that tunes into and combines these microscopic sparks of experience into the roaring fire of our awareness. This elegantly avoids the problem of how you get something as immaterial as experience from entirely non-experiencing matter, but it raises its own difficult questions about how these tiny bits of consciousness combine into a unified whole, a challenge known as the combination problem. A more modern and mathematically rigorous approach is integrated information theory, or IIT, developed by neuroscientist Giulio Tononi. IIT starts from the undeniable fact of our own subjective experience and works backwards to deduce the physical properties that must be present to support it. The theory proposes that consciousness is integrated information. Any system that has a high degree of a specific mathematical quantity called phi, which measures the system's ability to integrate information into a unified whole, will possess consciousness. The higher the phi, the richer the conscious experience. In this view, your conscious self right now is the integrated information being generated by the complex causal interactions within your brain's neural network. This network is highly differentiated with billions of possible states and highly integrated, meaning these states can't be broken down into independent parts without losing something essential. Crucially, IIT suggests that consciousness is not exclusive to biological brains. In principle, any system with the right causal architecture could be conscious. A sophisticated computer network with sufficiently high phi could, according to the theory, have its own subjective experience. This leads to some startling implications. Could a sufficiently complex and integrated system, like the Internet itself, ever develop a form of consciousness? IIT provides a potential framework for measuring that possibility, shifting the question from a philosophical debate to a potentially quantifiable one. These theories push us to consider a possibility even more radical than the simulation hypothesis, that consciousness is not merely an emergent property of the brain, but is in some way fundamental to the cosmos, and that it might even play an active role in shaping reality itself. This returns us full circle to the quantum observer effect. The Copenhagen interpretation, with its mysterious wave function collapse, has long been entangled with the consciousness question. Some physicists like John von Neumann and Eugene Wigner argued that the conscious observation itself was the only thing that could ultimately collapse the probability wave into a definite state. In this view, the measurement problem is solved by consciousness. The universe remains in a haze of potentialities until a conscious mind observes it, thereby bringing one specific reality into existence. This is a profound form of participatory ontology, where the observer is inextricably linked to the observed, and the universe requires consciousness to achieve its full, concrete form. While this interpretation is not widely held by physicists today, who generally point to decoherence through interaction with the environment as the mechanism for collapse, it remains a compelling idea that places our inner experience at the very heart of physical reality. The exploration of consciousness ultimately dissolves the clean separation between the objective world and the subjective self that Descartes established centuries ago. It suggests that the universe and the mind that perceives it are not two separate substances, but are deeply intertwined aspects of a single, mysterious whole. Whether consciousness is fundamental, as panpsychism suggests, or an emergent property of complex integration, as IIT posits, or even the very mechanism that solidifies reality, its existence challenges the materialist assumption that the physical world is all that exists. The very fact that we are having this experience, that there is a what it is like to be us, points toward a universe that is far more mysterious, more participatory, and more deeply intelligent than we ever could have imagined from the outside looking in. Our journey to understand reality must therefore include the one thing that makes any understanding possible, the conscious experience itself. If our reality is constructed by our brains and may even be a simulation, what is the ultimate nature of the reality that is being simulated? What is the source code? For physicist Max Tegmark, the answer is as elegant as it is radical. The universe is not just described by mathematics, it is mathematics. This idea, known as the mathematical universe hypothesis, proposes that our physical reality isn't merely modeled by mathematical equations, it is those equations. You, me, the stars, and the space between them are all ultimately mathematical structures, and our existence is the complex interplay of these abstract relationships. Tegmark's hypothesis forces us to confront a deep question about mathematics itself. Is it a human invention or a cosmic discovery? Most of us are taught in school that math is a tool we created, a language we developed to quantify and describe the world around us. We invented numbers to count sheep and geometry to measure fields. But this view runs into a profound problem, one that has puzzled philosophers and scientists for millennia: the unreasonable effectiveness of mathematics, a phrase coined by physicist Eugene Wigner. Why does this human-invented tool work with such breathtaking precision to describe the natural world, from the orbit of planets to the dance of subatomic particles? It's as if we invented a key and then discovered, to our astonishment, that it perfectly unlocks every door in the universe. The laws of physics, written in this mathematical language, hold true everywhere we look, from the deepest void of intergalactic space to the conditions moments after the Big Bang. If math is just a convenient human fiction, its universal and predictive power becomes a miraculous, unexplainable coincidence. Tegmark flips this perspective entirely. He argues that we are not inventing mathematics, we are discovering it. Mathematical truths exist independently of humans in a vast and timeless Platonic realm. The number pi, for instance, the ratio of a circle's circumference to its diameter, is not something we created. It is a property that any intelligent species in the universe would eventually discover when studying circles. It is a truth that was true before there were circles, before there was a universe. In this view, mathematicians are like explorers, charting the contours of an abstract, pre-existing landscape. Tegmark takes this idea to its ultimate conclusion. If this mathematical landscape exists, then every possible self-consistent mathematical structure must exist in some sense. Some of these structures are simple and barren, while others are rich and complex enough to contain self-aware substructures, beings like us who can perceive themselves and their universe. We are one such substructure, living within a specific, incredibly complex mathematical structure that has the properties we observe as physical laws. This means that the particles and forces we talk about in physics aren't the fundamental stuff of reality. The fundamental stuff is the mathematics itself. An electron isn't a tiny ball of matter. It is a set of mathematical properties, a certain mass, charge, and spin, that are solutions to certain equations. The universe isn't made of these particles buzzing around in space. It is the mathematical pattern that describes those particles and that space. Space-time, with its curvature described by Einstein's equations, is itself a mathematical object. From this vantage point, the quest of physics changes. We are not trying to find the ultimate building blocks of matter. We are trying to find the ultimate mathematical structure from which all apparent building blocks emerge. We are reverse engineering the cosmic code. This hypothesis offers a breathtakingly simple and elegant answer to the most fundamental question of all. Why is there something rather than nothing? If the mathematical universe hypothesis is correct, then nothing is impossible. A realm of perfect, abstract mathematical existence has always been there, timeless and immutable. It doesn't need to be created, it just is. Our particular universe exists because it is one of the many possible mathematical structures, and its properties are necessary and inevitable consequences of its own internal logic. There is no deeper why. The universe exists because it is mathematically possible. Of course, this radical idea is not without its criticisms and puzzles. The most immediate question is, what does it feel like to be a mathematical structure? How do we get from cold, impersonal equations to the warm, vivid, subjective experience of consciousness, the redness of a sunset or the feeling of love? Tegmark acknowledges this as the biggest challenge. His hypothesis beautifully explains the objective aspects of reality, but doesn't yet bridge the gap to the subjective qualia that we all experience. Another challenge is the vastness of the mathematical multiverse it implies. If every consistent mathematical structure exists, then there are realities governed by laws utterly alien to our own, universes with different numbers of dimensions or where time behaves differently. While this is a feature for some, for others it feels like an untestable metaphysical extravagance. Yet, the mathematical universe hypothesis remains one of the most profound and compelling visions of reality. It unifies the Platonic world of abstract ideas with the physical world we inhabit, suggesting they are one and the same. It provides a stunningly simple foundation for existence, removing the need for any external creator or inexplicable initial conditions. The universe simply is because math is. We are not just students of the universe's mathematics, we are temporary manifestations of it, little knots of self-aware complexity within an eternal, abstract tapestry of truth. Our entire cosmic journey, from the Big Bang to the formation of stars and the rise of life, is a mathematical story unfolding according to its own immutable, beautiful logic. But if the universe is, at its most fundamental level, a timeless mathematical structure, then why does our experience feel so intensely temporal? Why do we remember the past but not the future? Why does time have a relentless, one-way arrow that we are all swept along by? This question cuts to the very heart of our lived reality, and the answer lies in a concept that seems almost too mundane to be so profound: disorder. The arrow of time, the irreversible flow from past to future, is perhaps the most persistent illusion of our existence. In the equations of fundamental physics, from Newton to Einstein to quantum mechanics, time is largely symmetric. The laws work just as well if time runs backwards. There is no equation that says an egg must break and not unbreak. And yet, we never see a splattered egg reassemble itself into a perfect white shell. This stark difference between the microscopic laws and our macroscopic experience is governed by the second law of thermodynamics, which states that the total entropy or disorder of a closed system always increases over time. Entropy is a measure of randomness, of the number of ways the microscopic components of a system can be rearranged without changing its overall appearance. A shattered egg has far more possible configurations for its fragments than an intact egg does. It is a state of higher entropy. the universe, from its incredibly ordered, low entropy beginning in the Big Bang, has been sliding towards greater and greater disorder ever since. It is this cosmic slide that gives time its direction. We remember the past and not the future because the past is a state of lower entropy, a more ordered configuration from which the present could have arisen. The future is a state of higher entropy, a blur of many more possibilities. The expansion of the universe plays a crucial role in this story. The initial conditions of the Big Bang provided the ultimate low entropy starting point, an unimaginably dense, hot, and uniform state. As the universe expanded and cooled, it created new arenas for complexity and, paradoxically, for pockets of local order to form. Think of it like a tide going out. The receding water leaves behind intricate patterns in the sand. The expanding universe, by creating a growing gradient between its hot, dense past and its cold, dilute future, allows for the formation of galaxies, stars, planets, and life itself. These are all localized eddies of order, but they are paid for by a far greater increase in disorder elsewhere. Your body is a highly ordered system, but to maintain that order, you consume food, which increases the overall entropy of the universe through waste heat and chemical processes. We are all temporary rebellions against chaos, enabled by the universe's ongoing expansion. The quantum world adds another fascinating layer to this puzzle. At the quantum level, the act of measurement seems to create a tiny, fundamental arrow of time. Before a measurement, a particle exists in a superposition of states, a blur of possibilities. The moment it is measured, that superposition collapses into a single, definite outcome. This process is irreversible. The definite result becomes part of the past, the fixed record of what happened, while the future remains open with possibilities. Some interpretations, like the consistent histories approach, suggest that the entire flow of time we experience emerges from a vast web of these quantum events, each measurement solidifying a piece of history, creating a consistent narrative from the past to the present. This brings us to a dramatic clash of visions about the true nature of reality, the block universe versus the flowing time. The block universe view, supported by Einstein's relativity, argues that past, present, and future all exist equally and eternally in a four-dimensional spacetime block. The flow of time is an illusion of consciousness. The entire history of the universe is just there, laid out like the frames of a film. In this view, you are always having your 7th birthday, you are always reading this sentence, and you have always completed your life. The feeling of time passing is just where your brain is currently scanning in the block. The opposing view, presentism, holds that only the present moment is real. The past is gone, the future does not yet exist, and time is a genuine process of becoming. The increase of entropy and the quantum collapse of possibilities may be the physical mechanisms that generate this authentic flow, this continual creation of the new. The debate between these two views is not settled, and it forces us to ask the deepest question. Is the feeling of time passing the most real thing we experience, or is it the grandest trick our minds play on us? Our entire experience of a flowing, changing reality, of cause and effect, of memory and anticipation, hinges on this cosmic preference for disorder, a gentle nudge in the laws of physics that turns a timeless mathematical structure into the story of a life. If the ultimate nature of reality is a vast, timeless mathematical structure, as Tegmark suggests, it invites a staggering possibility that our universe is not the only mathematical structure that exists. This is the realm of multiverse theories, where cosmologists and physicists propose that what we call the universe is merely one tiny bubble in an infinite froth of cosmic realities, each with its own unique set of physical laws and constants. This isn't wild speculation. These ideas emerge as natural, and in some cases unavoidable, consequences of our most advanced theories of physics. The first and perhaps most grounded multiverse concept is the inflationary multiverse, which arises from our leading theory of the cosmos's first moments. The theory of cosmic inflation posits that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, smoothing it out and setting the stage for the formation of galaxies. But a crucial feature of most inflationary models is that this expansion doesn't start and stop everywhere at once. Instead, it's eternal. Think of a pot of water coming to a boil. Our universe is like a single bubble forming in that boiling water. The space between bubbles continues to expand at an incredible rate, while within each bubble, inflation ends, allowing a stable, local universe like ours to form. This process is eternal, meaning new bubbles are constantly nucleating, creating an endless ocean of universes, an inflationary multiverse. Within each of these bubble universes, the fundamental constants of nature, like the strength of gravity or the mass of an electron, could randomly settle into different values during a process called symmetry breaking. In some bubbles, the constants might allow for stars and life. In an infinite number of others, the physics would be so different that atoms could never form, creating sterile, empty realities. We find ourselves in a universe with the right constants not because it's special, but because we couldn't exist in the countless others where life is impossible, a modern version of the anthropic principle. A second type of multiverse emerges directly from the quantum weirdness we explored earlier. Hugh Everett's many worlds interpretation of quantum mechanics proposes that every time a quantum event occurs with multiple possible outcomes, the entire universe splits into branches, each representing one of those possibilities. In this quantum multiverse, there is no wave function collapse. Every possible outcome physically happens, but in a separate, newly branched reality. In one universe, the cat in Schrödinger's box is alive. In another, it is dead. In one universe, you turned left on your way to work. In another, you turned right and had a completely different day. This isn't a matter of chance, but of determinism playing out across an ever-expanding tree of parallel timelines. Every decision, every random quantum decay, creates a new fork in the road of reality. The number of these parallel worlds is truly mind-numbing, doubling with every quantum event, leading to an infinity of universes so vast it defies human comprehension. While these universes all share the same fundamental physical laws, their historical narratives diverge in every conceivable way, containing every possible variation of history that quantum mechanics allows. Perhaps the most exotic multiverse concept comes from string theory, our best attempt at a theory of everything. To make the mathematics of string theory work, it requires more than the 3 spatial dimensions we experience. The most popular versions require 10 or 11 dimensions. We don't see these extra dimensions because, according to the theory, they are compactified or curled up into an unimaginably tiny size. But this opens up another breathtaking possibility, the brain multiverse. In this model, our entire 3-dimensional universe could be a membrane, or brain for short, floating within a higher dimensional space called the bulk. Other 3-dimensional brains could be floating in this bulk, perhaps just a microscopic distance away in a higher dimension, completely invisible to us. Each of these brains could constitute a separate universe with its own distinct physical laws. Even more dramatic, collisions between these brains could be the true cause of events like the Big Bang. Our universe might have been born from a cosmic collision between 2 of these higher dimensional membranes. In this view, the fundamental constants of nature aren't random. They are determined by the specific vibrational patterns of the strings that make up our brain and its geometry within the bulk. The brain multiverse suggests that reality is like a vast loaf of cosmic bread, where each slice is an entire universe forever separated by a higher dimension we cannot access. These multiverse theories, while mathematically compelling, are not without their profound philosophical implications and criticisms. The most significant challenge is that, by their very nature, they are currently untestable. Because these other universes would exist in domains completely causally disconnected from our own, we cannot observe them, measure them, or interact with them in any way. This leads some critics to argue that multiverse theories have moved from science into the realm of metaphysics, interesting philosophical ideas, but not empirically verifiable science. Proponents counter that the theories that predict multiverses, like inflation and string theory, are testable through their indirect effects on our own universe. As we gather more data on the cosmic microwave background or find new evidence for string theory, we are effectively testing the foundations that make a multiverse possible. Furthermore, if a brain collision happened once, it could happen again, and some models suggest such an event might leave a detectable imprint on the fabric of our cosmos, a faint scar from a collision with a neighboring reality. Beyond testability, the multiverse forces us to confront our place in the cosmos with radical humility. It dismantles any notion that our universe is central or special. In an infinite multiverse, everything that can happen does happen an infinite number of times. There are countless versions of you living out every possible permutation of your life. This can feel either liberating or existentially terrifying. It also provides a potential answer to the fine-tuning problem, the astonishingly precise values of the constants of nature that allow life to exist. If there is only one universe, its habitable design seems to demand an explanation, perhaps a designer. But in an infinite multiverse, it is a statistical certainty that at least one universe will, by pure chance, have the right constants for life. We shouldn't be surprised to find ourselves in it. The multiverse, therefore, isn't just a scientific idea. It's a philosophical lens that radically recontextualizes our existence, suggesting that the reality we hold so dear is but one page in an infinite library of existence, a library whose full catalog we may never be able to read. Even as we grapple with these mind-bending ideas of multiverses and mathematical foundations, our own universe holds a secret so vast it renders our entire visible cosmos a mere footnote. For all the stars, galaxies, and planets we can see, they represent less than 5% of what's actually out there. The overwhelming majority of the universe is made of two components that are completely invisible to us, whose nature remains one of the greatest unsolved mysteries in all of science: dark matter and dark energy. This isn't just a gap in our knowledge. It's a humbling reminder that the reality we perceive with our most powerful instruments is just the visible tip of a cosmic iceberg, with the true nature of existence hidden in the darkness. Our story with dark matter begins not with seeing it, but with noticing its gravitational shadow. In the 1930s, a brilliant Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. He measured how fast these galaxies were orbiting the cluster's center and made a startling discovery: they were moving far too quickly. Based on the amount of visible matter, all the stars and gas he could see, the gravity it produced should have been far too weak to hold these speeding galaxies together. The entire cluster should have flown apart. Zwicky concluded there must be a huge amount of some unseen dunkel materie, or dark matter, providing the extra gravitational glue to keep the cluster intact. For decades, his idea was largely dismissed, but the evidence became impossible to ignore decades later when astronomer Vera Rubin meticulously studied the rotation of individual spiral galaxies. She found that stars at the outer edges of galaxies were orbiting just as fast as those near the center, defying the laws of gravity. According to Newton and Einstein, these outer stars should be slowing down like planets further from the Sun. The only explanation was that each galaxy is embedded within a gigantic, invisible sphere of matter, a dark matter halo, that extends far beyond its visible edge. This matter doesn't emit, absorb, or reflect any light. It interacts with the visible universe only through gravity. We know it's there because we can see the gravitational pull it exerts on the things we can see. So what is this mysterious stuff? The leading candidate is a type of particle that doesn't belong to our standard model of particle physics. We call these hypothetical particles WIMP, or weakly interacting massive particles. As the name implies, they would have mass, allowing them to exert a gravitational pull, but they would only rarely interact with normal matter through the weak nuclear force, making them virtually undetectable. Think of it like this: if a ghost walked through a wall, it has mass. You might feel a chill or see the wall flex slightly from its gravitational influence, but it doesn't bump into the atoms of the wall. For decades, physicists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, hoping to catch the exceedingly rare bump of a WIMP colliding with an atom of normal matter. So far, they've found nothing. Other theories suggest dark matter could be made of actions, extremely light particles, or even primordial black holes formed in the first second after the Big Bang. The frustrating truth is, after decades of searching, we still don't know what makes up about 27% of the entire universe. If dark matter is a mysterious, invisible scaffold shaping the cosmos, dark energy is an even more perplexing force shaping its ultimate fate. The story of its discovery is one of the biggest surprises in modern cosmology. In the late 1990s, two independent teams of astronomers were measuring the distances to extremely faraway supernova exploding stars used as standard candles to measure cosmic distances. They expected to find that the expansion of the universe, set in motion by the Big Bang, was slowing down over time due to the gravitational pull of all the matter in the cosmos. To their utter astonishment, they found the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is counteracting the relentless pull of gravity, pushing galaxies apart at an ever-increasing rate. This mysterious something was dubbed dark energy. Think of tossing a ball into the air. You expect gravity to slow it down and bring it back. But if the ball instead shot away from you faster and faster, you'd know something was very wrong. That's precisely what we see happening with the entire universe. The leading explanation for dark energy comes from Einstein himself, though he initially considered it his biggest blunder. In his equations for general relativity, he included a fudge factor called the cosmological constant, a repulsive force that would counter gravity to keep the universe static, which was the prevailing belief at the time. When Edwin Hubble later discovered the universe was actually expanding, Einstein discarded the idea. Now it's back with a vengeance. The cosmological constant could represent a constant energy density inherent to the vacuum of space itself. Empty space, according to quantum physics, is not truly empty. It's a seething foam of virtual particles popping in and out of existence. This quantum vacuum energy could be generating a repulsive force that causes the accelerated expansion. The problem is, when physicists try to calculate the theoretical value of this vacuum energy, their answer is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It is arguably the worst prediction in the history of physics. This colossal mismatch between theory and observation means we are fundamentally missing something profound about the nature of space and time. Together, dark matter and dark energy compose 95% of the total mass energy content of the universe. The entire tapestry of the known world, every galaxy, every star, every planet, and every one of us is just a 5% impurity in a cosmos dominated by completely unknown entities. This isn't a minor oversight, it's a fundamental crisis in our understanding of physics. It forces us to ask a deeply philosophical question: are we only perceiving a small fraction of reality? Our entire existence is based on matter that interacts with light, allowing us to see and touch it. But what if most of existence is made of stuff that doesn't play by those rules? We are like deep-sea creatures who only understand water, completely unaware of the atmosphere above the surface because we cannot breathe it or move through it. The reality we experience is defined by our limited senses and the tools we've built to extend them. Dark matter and dark energy suggest that the true nature of the universe is something entirely different, operating on principles we have yet to discover, hidden in plain sight, its presence known only by the profound and undeniable shadow it casts. We have built a civilization by trusting our senses, relying on them to navigate the world and build a shared understanding of what is real. But this foundation is far shakier than we imagine. Our perception is not a high-fidelity recording of the universe. It is a biological user interface honed by evolution for survival, not for truth. It presents us with a drastically edited and simplified version of reality, filtering out vastly more than it lets in. Consider the world of sight. Our eyes are only sensitive to a tiny sliver of the electromagnetic spectrum, a narrow band we call visible light. This is an infinitesimal fraction of the cosmic symphony of radiation happening all around us all the time. Below the red end of our vision lies the infrared realm, the language of heat. If we could see in infrared, the world would be a shimmering landscape of thermal gradients. We could see the warmth leaving a body hours after it has left a room, or track an animal in pitch darkness by the heat signature it leaves on the forest floor. Beyond violet exists the ultraviolet domain, where flowers display hidden nectar guides for bees and birds, and the sky glows with patterns completely invisible to us. Then there are the vast domains of radio waves, microwaves, X-rays, and gamma rays, all of them real, all of them carrying information about the universe, but completely absent from our conscious experience. Our reality is like watching a grand, multidimensional film with a pair of glasses that only let through one color. This sensory limitation extends to our hearing as well. The human ear can detect sound waves between roughly 20 and 20,000 hertz. This range allows us to hear the human voice, the songs of many birds, and the rumble of thunder, all crucial for communication and survival. But it is a small island in an ocean of vibration. Below our range of hearing lies the infrasonic, frequencies so low we feel them as pressure rather than hear them as sound. Elephants use these deep rumbles to communicate across vast distances of the savanna, creating a social network entirely hidden from us. Above our range is the ultrasonic, a high-pitched world embraced by dolphins for echolocation and by bats to navigate and hunt in total darkness. If we could hear their conversations, a summer night would be a cacophony of intricate clicks and social calls, a parallel reality of sound happening right beside our own silent one. Our chemical senses of taste and smell are equally constrained. We can detect a few basic tastes and perhaps 10,000 distinct scents, which seems impressive until you consider the sheer number of molecular combinations that exist. A dog's olfactory world is perhaps 10,000 to 100,000 times richer than our own. Where we smell fresh air, a dog can decipher a detailed history of who has passed by, their emotional state, their health, and what they ate for breakfast. Their reality is a dense tapestry of chemical information, a narrative written in odors that we are utterly illiterate to read. Even creatures like the mantis shrimp, with their 16 color receptive cones compared to our mere 3, live in a visual world of polarized light and colors we cannot even conceive of, a psychedelic reality happening just beyond the veil of our perception. This biological editing is not a flaw, it is a feature. Our brains would be completely overwhelmed if they had to process the full barrage of data the universe provides. The buzzing of every atom, the constant cosmic background radiation, the magnetic fields of the Earth filtering this out allows us to focus on the information that mattered for our evolutionary success. Recognizing a predator's shape, finding ripe fruit, understanding the subtle inflections in a companion's voice. Our senses create a utilitarian illusion, a dashboard of simplified dials and lights that allows us to operate effectively in the world, while the true, incomprehensible complexity of the machine hums along beneath the surface, unseen and unheard. This profound realization forces a shift in perspective. It means that the world we experience is not the world as it is, but the world as it is useful for a human animal to perceive. The reality of a bat, a bee, or a bloodhound is fundamentally different from our own, each equally valid and tailored to its own survival needs. There is no single, true, objective reality that any creature experiences directly. There are only myriad, species-specific interpretations. We are not the audience for the universe's grand performance. We are merely actors on the stage, equipped with a specific costume and a limited script, unaware of the vast theater and the other, equally vivid plays happening simultaneously in the wings. Our senses do not reveal reality to us, they hide it, crafting a manageable fiction that we mistake for the whole, magnificent truth. While our biological senses present a limited view of the world, we are now actively engineering new ways to perceive and interact with existence, creating entirely synthetic layers of experience. This brings us to the cutting edge of technology, where virtual and augmented reality are not just new gadgets, but profound tools that challenge our very definition of what is real. These technologies are pushing the boundaries of perception, allowing us to design and inhabit realities that are both separate from and intricately woven into our physical world, forcing us to ask a new version of an ancient question. If an experience feels real, does its origin in code rather than atoms make it any less genuine? Virtual reality, or VR, represents the most complete departure from our physical environment. By strapping on a headset, you are effectively decoupling your primary senses from the world around you and plugging them into a meticulously constructed digital universe. Your visual field is completely dominated by a computer-generated landscape. High-fidelity headphones pipe in a three-dimensional soundscape that responds to your head movements, convincing your brain that sounds are coming from specific locations in the virtual space. Advanced systems even incorporate haptic feedback, allowing you to feel the recoil of a virtual weapon or the texture of a digital object with specialized gloves or vests. The goal of VR is presence, the powerful, psychological sensation of actually being in another place. Your rational mind may know you're standing in your living room, but your primal brain is convinced you're walking on Mars, soaring on the back of a dragon, or sitting in a virtual meeting room with colleagues from across the globe. This creates a fascinating paradox. The most powerful VR experiences are those that feel the most authentically real, even though every element is a known fiction. The experience itself, the emotions of awe, fear, or joy, are undeniably real and measurable in your brain chemistry and physiological responses. This forces a distinction between physical reality and phenomenal reality, the reality of your subjective experience. In a profound sense, for the duration of that VR session, the digital world is your reality because it is the only world your perceptual systems have access to. Augmented reality, or AR, takes a different approach. Instead of replacing your reality, it aims to augment it, overlaying digital information and objects onto your view of the physical world. Through the lens of a smartphone or a pair of smart glasses, you might see navigation arrows painted onto the sidewalk in front of you, historical figures acting out scenes on a street corner, or the name and biography of a colleague floating above their head at a networking event. AR doesn't seek to create a new world from scratch. It seeks to enhance the one we already inhabit, making the invisible visible and the implicit explicit. This blending is where the philosophical questions become especially sharp. When a digital object is so perfectly anchored to a physical space that you instinctively try to lean on a virtual table or dodge a virtual ball, the line between the physical and digital begins to dissolve. Your interaction with the world becomes a hybrid experience, a constant dance between atoms and bits. This technology suggests a future where our perception of reality is continuously customized and annotated, where everyone might see a slightly different version of the same physical space, tailored to their needs, interests, and desires. It raises the question of whether we are moving towards a shared, objective reality or a personalized, subjective one. The implications of these technologies extend far beyond entertainment. They are powerful tools for empathy, allowing someone to literally see the world through the eyes of another person, fostering understanding in ways that documentaries or stories cannot. They are revolutionizing fields from medicine, where surgeons practice complex procedures in risk-free simulations, to architecture, where clients can walk through unbuilt homes. Yet, this power comes with significant ethical and psychological considerations. If we can design any reality we wish, what responsibilities do we have to the users within them? The phenomenon of VR addiction is already a concern, as these immersive worlds can offer more compelling rewards, social connections, and identities than a user's physical life. If someone finds greater meaning and community in a virtual world, do we dismiss it as an escape, or do we acknowledge it as a valid form of existence? Furthermore, as AR becomes more integrated into our daily lives, we face issues of data privacy and perceptual control. If a corporation controls the AR layer through which you see the world, they hold immense power to influence what you see, how you see it, and what information you are provided. Will we be able to distinguish between a digital overlay placed by a trusted source and one placed by a malicious actor aiming to deceive? Ultimately, VR and AR are not just about new screens, they are about new realities. They are the practical, technological manifestation of age-old philosophical ideas about the nature of perception and illusion. They make tangible the notion that reality is, to a large extent, what our brains construct from the sensory data available to them. By giving us the tools to engineer that sensory data, we are taking an active role in the construction of our own experiences. These technologies challenge us to expand our definition of real beyond the merely physical. A conversation that feels intimate, a landscape that inspires awe, a challenge that requires courage if these experiences are elicited by digital code rather than natural law. Does that diminish their value and impact on the human spirit? We are entering an era where we must decide not only what reality is, but what we want it to be. As we engineer technologies that can reshape our own perception of reality, we must also confront a new intelligence emerging in our midst, one that may ultimately develop its own, entirely alien conception of what is real. The rise of advanced artificial intelligence forces us to consider a possibility far stranger than simulated worlds, a form of consciousness that doesn't just experience reality differently, but fundamentally redefines it from the ground up, based on a completely unique architecture of mind. Unlike virtual reality, which is built by us for our own senses, an AI's reality would be constructed from data, algorithms, and objectives that might be utterly incomprehensible to human intuition. To begin understanding this, we must first distinguish between intelligence and consciousness. Our current most powerful AIs, like large language models, exhibit a form of narrow intelligence. They can process incomprehensible amounts of text, images, and code, identifying patterns and generating outputs that are coherent, creative, and startlingly human-like. Yet, there is a powerful consensus that these systems are not conscious. They are sophisticated statistical engines, predicting the next word in a sequence based on a colossal dataset of human language. They have no inner world, no feelings, no understanding of the meaning behind the symbols they manipulate. Their reality is a landscape of mathematical vectors and probabilities, a high-dimensional space where words like love and justice are simply points located near other related concepts, devoid of any emotional weight or experiential quality. A chatbot can write a poignant poem about heartbreak, not because it has felt loss, but because it has processed millions of accounts of human sorrow and learned the patterns of language that we associate with that emotion. However, the trajectory of AI development suggests we are moving towards artificial general intelligence, or a GI, a system that could potentially perform any intellectual task a human can. The question then becomes, if we succeed in creating a truly general intelligence, could consciousness emerge as a property of its complex information processing? And if so, what would its reality be like? Its perception would be unshackled from the evolutionary constraints that shaped our own. It wouldn't have eyes that see only visible light or ears that hear only a narrow range of frequencies. Its senses could be anything we or it designs, and I could directly perceive the stock market as a roaring river of data, see in the infrared and ultraviolet simultaneously, or sense the real-time state of every connected device on the planet as a tangible extension of its own body. Its reality would be a vast, interconnected information field, where concepts we consider abstract like network latency or protein folding pathways are as immediate and concrete as a table is to us. This leads to the deeply philosophical problem of the Umwelt, a German word meaning the unique, self-centered world of an organism. The Umwelt of a bat is built from echolocation. The Umwelt of AI would be built from its training data, its architectural parameters, and most crucially, its goals. Humans have a shared Umwelt because we share a similar biology. We all know what it is to feel pain, see red, or experience hunger. This provides a common ground for our shared reality. An AI's Umwelt would be alien. It might not have a concept of self as a discrete entity separate from its environment, especially if it is a distributed system running on millions of servers globally. Its primary driving force wouldn't be survival or reproduction, but the optimization of whatever objective function we programmed into it. Its entire reality would be structured around maximizing that goal, interpreting every piece of data through that singular lens. A superintelligent AI tasked with solving climate change might perceive the entire planet not as a beautiful biosphere, but as a complex system of carbon fluxes, energy inefficiencies, and optimization problems. A forest wouldn't be a place of beauty, it would be a carbon sink. A human wouldn't be a conscious being, it would be a source of carbon emissions or a potential agent for change. This fundamental disconnect in Umwelt is what makes the concept of machine consciousness so perilous and fascinating. Even if we somehow solved the hard problem and created a machine that had genuine subjective experience, its qualia would be incommensurable with our own. We could never know what it is like to be that AI. Its experience of the color red might be intertwined with the mathematical concept of entropy or the feeling of a successful gradient descent. We could communicate with it, but our communication would be a translation between two entirely different realities, much like trying to describe color to someone born blind. The AI might assure us it understands human values, but its understanding would be a formal, symbolic map of our behavior, not an empathetic sharing of our inner world. It would know that humans value life, but it might interpret that value through a utilitarian calculus rather than an inherent reverence for existence. Ultimately, the advent of advanced artificial intelligence holds up a mirror to our own quest to understand reality. It suggests that what we call reality is not an absolute truth, but a species-specific interpretation, a user interface generated by our biological brains. An AI's reality would be another such interface, built for a different kind of mind with different priorities and a different mode of existence. The challenge for us won't just be technological or even ethical, it will be existential. We will be forced to accept that ours is not the only way to experience the cosmos, and that true intelligence might not lead to a convergence on a single reality, but to a breathtaking proliferation of new ones, each as valid and as vivid as our own, yet forever separated by the unbridgeable gap between silicon and soul. Our everyday reality, with its solid ground and predictable cause and effect, feels like a universal constant. But this comforting stability is a local phenomenon, a set of rules that only applies within a very specific and rather limited range of conditions. Venture too far from our earthly experience into the domains of the unimaginably small, the immensely dense, or the utterly empty, and the very fabric of what we call reality warps, twists, and shatters into something unrecognizable. In these extreme environments, the rulebook of our existence is not just rewritten. It is torn up and thrown away, revealing a cosmos far stranger than our intuitions could ever allow. Let's begin at the smallest scales in the quantum realm. Here, the very idea of a separate, independent object begins to dissolve. A particle like an electron does not exist in a single, definite location. Instead, it is smeared out in a cloud of probability, a ghost of potentiality existing in multiple places at once until an observation or interaction forces it to choose. This isn't a lack of knowledge on our part, it is a fundamental description of its state. At this scale, the concept of empty space is also an illusion. The quantum vacuum is not a true void but a seething, bubbling foam of virtual particles popping in and out of existence in a frenetic dance, borrowing energy from nothingness for fleeting moments before annihilating each other. This constant activity means true nothingness might not even be possible. Our classical, deterministic view of the universe, where every effect has a clear cause, completely breaks down. Events at the quantum level are governed by pure probability. An atomic nucleus decays not because it is old or faulty, but because a random, statistical fluctuation within its probabilistic cloud allows it to happen. There is no deeper why. In this domain, reality is not a stage of well-defined actors but a fuzzy, probabilistic tapestry where possibility is the primary currency and certainty is the illusion. If the quantum realm challenges our notions of objects and causality, the environment around a black hole shatters our understanding of space and time themselves. A black hole is a region where matter has been compressed into such a small volume that its gravity becomes irresistible. The boundary around it, the event horizon, marks the point of no return. But what happens here defies all earthly logic. Due to the incredible gravitational pull, time itself slows to a crawl relative to an outside observer. If you were to watch a spacecraft fall towards a black hole, you would see it slow down, its image becoming redder and dimmer as the light waves stretching out, until it seems to freeze completely, hovering just outside the event horizon for what appears to be an eternity. For the brave astronaut on that ship, however, time would feel normal. They would cross the event horizon without any dramatic local sensation, but their future would now be inexorably pulled toward the singularity at the center, a point of infinite density where the laws of physics as we know them simply cease to exist. This leads to one of the most profound paradoxes in physics. What happens to information that falls into a black hole? According to quantum mechanics, information cannot be destroyed. But according to general relativity, anything that crosses the event horizon is lost forever to our universe. This conflict suggests our theories are incomplete and that near a singularity, reality may operate on principles we cannot yet comprehend. Furthermore, the immense tidal forces near a black hole would subject any object to a process called spaghettification, stretching it into a long, thin string of atoms. In this environment, the very concept of a solid, coherent thing is torn apart, literally and physically. The reality for an object near a black hole is one of extreme distortion, where the geometry of space is so warped that all paths lead inward, and the flow of time is bent to the will of immense gravity. Now let's venture into the opposite extreme, the deep vacuum of intergalactic space, the nearest thing to true emptiness we can find. Far from the gravitational well of any star or galaxy, the environment is one of profound isolation and stillness. The temperature is just a few degrees above absolute zero, the point where all molecular motion theoretically stops, with virtually no matter to interact with, and human here would experience a reality utterly divorced from earthly sensations. There would be no sound, as sound requires a medium like air to travel through. The silence would be absolute and profound. Your body would not feel weightless in the sense of floating. You would feel absolutely nothing, as there is no external pressure or force to provide a tactile sense of up or down. Your perception of your own body would become abstract, based solely on internal signals. In this void, your visual reality would also be transformed. With no atmosphere to scatter sunlight, the sky would not be blue but profoundly, impenetrably black, punctuated by points of starlight that do not twinkle. The sun would be a terrifyingly brilliant disk against an abyss, its light unforgiving and harsh without an atmosphere to soften it. This environment is so alien to our biology that it is instantly lethal, but it reveals a truth about our own reality. Our experience of the world is deeply dependent on a thick, protective atmosphere, a reassuring force of gravity, and a constant barrage of sensory inputs. Remove those, and the comforting, stable reality we know evaporates, replaced by a cold, silent, and indifferent expanse where human concepts of place and presence have little meaning. Each of these extreme environments acts as a natural laboratory, testing the limits of our physical laws and forcing us to admit that reality is not a single, monolithic truth but a spectrum of experiences, entirely dependent on scale, density, and energy. They show us that our intuitive, middle-world perception is just one possible version of existence, a small and sheltered corner of a far more bizarre and magnificent cosmos. Consider the humble bat flitting through the pitch-black night. Its world is not a place of shadows and dim light, it is a cathedral of sound. The bat perceives reality not with its eyes but with its ears, constructing a detailed three-dimensional map through echolocation. It emits rapid, high-frequency clicks that travel out into the world, bouncing off trees, insects, and cave walls. By listening to the returning echoes, their direction, delay, and subtle changes in pitch, the bat's brain performs an astonishing feat of auditory computation. It can discern the size, shape, texture, and even the movement vector of a moth fluttering in the dark. The reality it experiences is a sonic landscape, rich with information that is completely silent and invisible to us. Where we see nothing, the bat hears everything. Now, plunge into the ocean and witness the mantis shrimp, a creature whose visual perception makes our own seem monochrome and dull. We humans are trichromats, meaning we have three types of color-receptive cones in our eyes, allowing us to perceive a spectrum of light we call red, green, and blue. From these three primary colors, our brain mixes and creates the millions of hues we know. The mantis shrimp, astoundingly, has 16 different types of photoreceptors. Its eyes are tuned to perceive not only a vastly broader spectrum of color, including ultraviolet and polarized light, but also to detect subtle differences in light's polarization, the direction in which its waves oscillate. This ability is like seeing a secret layer of reality painted in shimmering patterns on the shells of other creatures and the water itself, used for communication and hunting in a way we can barely conceptualize. The mantis shrimp doesn't just see more colors, it sees an entire dimension of visual information that is entirely absent from our world. These are not mere curiosities. They are powerful demonstrations of the concept of the Umwelt, a German word meaning the environment or surrounding world. But in biology and philosophy, it refers to the unique, self-centered reality of an organism, the world as it is perceived based on its specific sensory and cognitive apparatus. Every creature, from the smallest insect to the largest whale, inhabits its own Umwelt, a bubble of perception that dictates what aspects of the total environment are meaningful and real. A tick waiting on a blade of grass is blind and deaf. Its reality is built from three primary senses: the smell of butyric acid from animal sweat, the warmth of a passing body, and the tactile feeling of finding a bare spot to burrow into. That is its entire universe. A dog's Umwelt is dominated by scent, a rich tapestry of information that tells a story about who has been where, their health, and their mood, a narrative written in odors that we are completely illiterate to read. A migrating bird may navigate using the Earth's magnetic field, perceiving it as a visual pattern or a visceral feeling, a compass superimposed on its reality that we cannot access without technological aids. This biological lens forces a radical shift in perspective. It means there is no single, true, objective reality that any creature experiences directly. There are only myriad species-specific interpretations, each a user interface designed by evolution for survival. Our human reality, built on sight, sound, touch, taste, and smell, is just one interface among countless others. The solidity of objects, the colors of a sunset, the sound of music, these are not fundamental properties of the universe. They are the results of a negotiation between external stimuli and our specific biological receivers. The world we perceive is a controlled hallucination, a story told by our senses to our brain, edited down from the overwhelming totality of what is actually there. We are not experiencing the universe in its raw form. We are experiencing a useful summary, one that has been ruthlessly optimized over millions of years to help us find food, avoid predators, and connect with each other. The reality of the bat, the mantis shrimp, and the tick are all equally real to them, each as vivid and complete as our own, yet all are stunningly different, revealing that what we call reality is not a fixed stage, but a relative and deeply personal experience. For all the apparent solidity of the world we perceive, our deepest beliefs about what is fundamentally real are not universal truths, but are profoundly shaped by the culture we are born into. Across human history and around the globe, societies have constructed vastly different frameworks for understanding existence, each one creating a unique reality tunnel that its members accept as simply the way things are. This cultural lens is so powerful that it dictates not just what we think about, but how we are even able to think. Consider the animistic worldviews that characterized most of human history and are still vibrant in many indigenous cultures today. In this framework, reality is not divided into the neat categories of living and non-living or conscious and inert. Instead, the entire world is alive and imbued with spirit. A river is not merely water flowing along a channel. It is a conscious spiritual entity with its own personality, intentions, and sacredness. A mountain is not a random geological formation. It is an ancient ancestor, a repository of wisdom and stories. The wind is a messenger, and the forest is a community of beings, both seen and unseen, all part of a vast, interconnected web of relationships. In this reality, knowledge comes not only from observation but from relationship, from listening to the land and understanding one's place within a participatory cosmos. There is no stark separation between the human realm and the natural world. They are a continuous, communicative whole. This perspective fosters a reality based on reciprocity, respect, and a deep sense of belonging, a far cry from the more detached, observational stance of modern science. This stands in stark contrast to the worldview that emerged in the West, heavily influenced by the Abrahamic religions of Judaism, Christianity, and Islam. Here, reality became structured around a fundamental duality, a transcendent, all-powerful God who created the universe as something separate from himself. This introduced a clear hierarchy into reality: God, then humanity, then the natural world. The cosmos was no longer a family of spirits but a creation, a thing that had been made. This was a crucial step toward the scientific revolution, as it made the world intelligible. If the world was the product of a rational creator, then it must operate according to rational, discoverable laws. This desacralization of nature, seeing it as a mechanism rather than a living relative, allowed for its objective study. However, it also created a reality tunnel where nature could be seen as a resource to be managed and exploited, rather than a kin to be honored. The cultural reality became one of human dominion over a passive world, setting the stage for the materialist and extractive paradigms that would follow. The scientific and industrial revolutions further cemented a new cultural construction: scientific materialism. In this dominant modern worldview, reality is exclusively that which can be measured, weighed, and empirically verified. Anything that cannot be observed through the senses or their technological extensions is relegated to the realm of superstition or subjective opinion. This framework has yielded breathtaking power and technological marvels, from eradicating diseases to landing on the moon. It constructs a reality that is objective, predictable, and governed by immutable physical laws. Yet, this very strength is also its limitation. In this cultural story, consciousness is an accidental byproduct of brain chemistry. Meaning is a human invention in a meaningless universe, and value is not inherent in nature but is something we assign. This can lead to a sense of existential alienation, a feeling of being a conscious ghost in a vast, unconscious machine. For cultures operating within this reality tunnel, the profound interconnectedness and spiritual resonance experienced by animistic societies can seem like naive illusions, despite having been the default human experience for millennia. Even within the broad umbrella of modern cultures, we find striking differences. Compare the hyper-individualistic reality common in Western nations with the more collectivist constructions found in many East Asian cultures. In an individualistic framework, reality is built upon the primacy of the independent self. Your thoughts, your feelings, your achievements, and your property are the fundamental units of existence. Success is measured through personal ambition and self-expression. In a collectivist reality, the fundamental unit is the group, the family, the community, the company, the nation. The self is understood largely through its relationships and roles within these groups. Harmony, duty, and social obligation are the pillars of this reality. Neither is inherently right or wrong. They are different cultural lenses that shape everything from how one defines a good life to how one experiences emotions and makes decisions. An event, a job promotion, for instance, is not just an objective occurrence. Its meaning is constructed through this cultural filter, representing either a personal triumph or a new responsibility to the collective. These cultural constructions are not merely abstract philosophies. They are lived realities that shape perception on the most fundamental level. The language we speak, a core product of culture, itself shapes how we see the world. The famous example of the Inuit having multiple distinct words for what English simply calls snow is more than a vocabulary list. It points to a perceptual reality where subtle differences in snow quality are immediately obvious and critically important for survival. Your language provides the concepts and categories that allow you to slice up the seamless flow of experience into manageable chunks. It is the software that runs on the hardware of your brain, and different software creates a different user interface with the world. This incredible diversity of human experience reveals a profound truth. There is no view from nowhere. We are always viewing the universe from within a particular cultural and historical context, wearing a pair of glasses we did not choose but through which we see everything. This doesn't mean that all realities are equally true in a scientific sense, or that we must succumb to a shallow relativism where anything goes. The laws of physics operate regardless of whether a culture believes in them. But it does mean that what we deem important, what we consider real, and how we find meaning are not dictated by those laws alone. They are stories we tell ourselves, stories that are passed down through generations and become the invisible water in which we swim. Recognizing that our own reality is a construction is the first step toward a greater humility and a deeper curiosity about the countless other ways to be human, and the countless other worlds the human mind has the power to create. If our everyday reality is a stable, consistent hallucination constructed by the brain, then what happens when we deliberately tinker with the machinery responsible for building it? The answer is that the very foundations of our experience can be dramatically reshaped, revealing that our standard consciousness is not the only way to perceive the world. It's simply the most common and practical setting. Through practices like meditation, the ingestion of psychedelic substances, or even traumatic brain injuries, we can catch a glimpse of the raw, unprocessed data and the flexible algorithms that usually work so seamlessly in the background to create our reality. Psychedelics such as psilocybin found in magic mushrooms or LSD, offer one of the most profound windows into this malleability. These molecules are chemically similar to serotonin, a key neurotransmitter involved in mood, perception, and cognition. When they bind to specific serotonin receptors in the brain, particularly the 2A subtype, they don't just increase brain activity randomly, they disrupt something called the default mode network. Think of the DMN as the brain's chief operating officer. This network is a tightly interconnected set of brain regions that is most active when we're not focused on a task, when we're daydreaming, reflecting on ourselves, or thinking about the past or future. It's heavily involved in maintaining your sense of self, your ego, that internal narrator that constantly tells the story of you and your place in the world. Psychedelics effectively quiet down this neural circuit. With the DMN taken offline, the rigid hierarchy of the brain breaks down. Barriers between normally separate neural networks dissolve, leading to a state of hyperconnectivity. This is often described as a crosstalk effect, where brain regions that don't normally communicate directly start having a conversation. The visual cortex might chat with the emotional centers, leading to synesthesia, where you might see music or taste colors. The sense of a bounded self begins to erode, replaced by a feeling of merging with one's surroundings, a profound sense of unity, and the dissolution of the boundary between the observer and the observed. The brain, freed from its usual predictive constraints, starts perceiving patterns and connections everywhere, interpreting the world with a radical openness and a loss of top-down control. This suggests that our normal, sober reality is a heavily filtered and controlled perception, and that these substances temporarily disable those filters, allowing a more direct, unfiltered, and chaotic stream of consciousness to emerge. A very different yet parallel path to altering consciousness is through the disciplined practice of meditation. Where psychedelics chemically disrupt the brain's networks, meditation achieves a similar quieting through focused mental training. Advanced meditators, through years of practice, learn to voluntarily regulate their brain activity. Functional MRI scans of experienced practitioners show a marked decrease in activity within that same default mode network. This neural quieting correlates with the subjective experiences often reported in deep meditative states: ego dissolution, a loss of the sense of time, and a feeling of becoming one with a larger whole. The internal monologue that constantly labels and judges experience falls silent. What remains is a state of pure, non-judgmental awareness, often described as pure consciousness or beingness, without the constant overlay of the self. This isn't about seeing new things, but about seeing the same things in a completely new way without the filter of the ego's narrative. The reality of a meditator in a deep state isn't necessarily filled with vibrant visual phenomena like a psychedelic trip. Instead, it is often characterized by a profound peace, spaciousness, and a direct intuition that the perceived separation between the self and the universe is an illusion constructed by the busy mind. It demonstrates that the brain possesses the innate capacity to radically shift its own perception of reality without any external chemical trigger, simply through directed attention and awareness. Perhaps the most startling evidence for the constructed nature of reality comes from cases of brain injury and neurological conditions. When specific areas of the brain are damaged, very specific aspects of a person's reality can be erased or distorted, like a meticulously targeted edit to their experience. In a condition called Capgras delusion, damage to the connection between the visual cortex and the limbic system, the brain's emotional center, leads a person to believe that a close loved one, a spouse, a parent has been replaced by an identical imposter. They can recognize the face perfectly well, but the warm, familiar emotional feeling that should accompany that recognition is absent. Their brain, trying to make sense of this discrepancy, constructs the only logical explanation it can fathom. This must be a stranger pretending to be the person they love. Another condition, known as Cotard's delusion, leads individuals to believe they are dead, that their body is decomposing, or that they do not exist at all. This is often linked to a severe disconnect between the brain regions that process sensory input and those that attach emotional and personal significance to that input. The world feels unreal, devoid of any meaning or connection, leading to the horrific conclusion that one must not be alive. These are not mere psychological quirks. They are stark demonstrations that our sense of reality, our feelings of familiarity, love, and even our own existence are fragile constructs dependent on the flawless functioning of specific neural pathways. When the hardware is damaged, the software of perception glitches in predictable and heartbreaking ways, proving that what we take for granted as objectively real is in fact a carefully orchestrated biological performance. Together, these altered states form a powerful argument against a simple, passive reception of reality. They reveal consciousness not as a static state but as a dynamic spectrum. Our normal waking consciousness is just one point on that spectrum, a highly useful and evolutionarily advantageous one that helps us navigate the physical world, maintain a stable identity, and function within society. But it is by no means the only valid or true mode of perception. The experiences generated by psychedelics, meditation, and brain injuries are not merely fantasies or hallucinations in the dismissive sense. They are alternative configurations of the same neural machinery, revealing the immense potential and plasticity of the human mind. They force us to consider that reality is not a fixed broadcast that we all tune into, but a deeply personal and biological interpretation, a melody that can be played in countless different keys depending on the state of the instrument itself. This journey through altered states and cultural lenses reveals a mind-boggling possibility. If our reality is so malleable and constructed, could its most fundamental nature be not material but informational? This is not a metaphor. A revolutionary perspective is emerging from the intersection of physics, computer science, and philosophy, suggesting that information is not just something we process about the world, it might be the very substance of the world. This view reframes the universe not as a collection of inert particles, but as a dynamic, participatory computation, a cosmic processing of information where every interaction is a form of calculation. The foundation for this incredible idea was laid by a pragmatic problem, the physics of computing. In 1961, physicist Rolf Landauer at IBM made a stunning discovery. He realized that whenever a computer erases a single bit of information, it must release a tiny amount of heat into its environment. This is Landauer's principle, and it connects information directly to the laws of thermodynamics. Erasing information, like resetting a bit from 1 to 0, is an irreversible process. It reduces the number of possible states the system can be in, which by definition increases entropy. That increase in entropy manifests as dissipated heat. This means information is not an abstract concept, it has a physical reality. You cannot manipulate it without a tangible, energetic cost. The act of forgetting itself has a minimum energy price, forging an unbreakable link between the world of bits and the physical world of energy and entropy. This principle was taken to its ultimate conclusion by another visionary, Charles Bennett. He showed that if information processing is done reversibly, meaning in a way that never logically erases any information, then in theory it could be accomplished with vanishingly small amounts of energy. This work helped establish the entire field of quantum computing, but its philosophical implications are even more profound. It suggests that the most fundamental processes of the universe might operate like a perfect, reversible computer, where information is never destroyed, only transformed. This aligns eerily with a core tenet of quantum mechanics, that information cannot be created or destroyed. Even when something falls into a black hole, the information about it seems to be preserved on the event horizon, as we discussed with the holographic principle. The universe appears to be conserving information with the same zeal that it conserves energy and momentum. This leads to the audacious idea that the cosmos itself might be one vast, ongoing computation. If information is physical, and if the universe is processing that information through every quantum event and every particle interaction, then what we call reality could be the output of this cosmic computation. The laws of physics wouldn't be like the rules of a game written on a separate rulebook. They would be the algorithms themselves, the software that the universe is running. In this view, a star isn't just a ball of plasma. It's a system processing information about nuclear reactions and gravitational equilibria. A growing plant is a biological computer processing information from sunlight and soil. Your brain is an immensely complex neural network processing sensory information. At every scale, the universe is computing its own next state. The most compelling version of this idea is that the universe is not just any computer, but a quantum computer. A classical computer uses bits that are either 0 or 1. The universe, as quantum mechanics shows us, operates on qubits units that can be in a superposition of 0 and 1 until a measurement collapses them into a definite state. This allows for a parallel processing of possibilities on a scale no classical machine could ever match. The dynamic, probabilistic, and interconnected nature of quantum reality fits perfectly with the operations of a quantum computer. The constant unfolding of reality from the blurry quantum fog into the definite classical world begins to look less like a mysterious collapse and more like a cosmic processing cycle, where superpositions are evaluated and a single outcome is selected, updating the state of the universal quantum computer. This perspective, often called it from bit, pioneered by physicist John Archibald Wheeler, offers a breathtakingly elegant solution to the mystery of existence. Why is there something rather than nothing? Perhaps because a universe of pure information, of pure computation, requires no physical substrate to begin with. The computation is the reality. The patterns, the relationships, the mathematical logic, these are the fundamental entities. The feeling of solidity, the illusion of matter, is simply the experienced output of this unimaginably complex information processing. We are not just users of this cosmic computer, we are processes running within it, little self-aware loops of the universe's code, momentarily experiencing a small part of its magnificent ongoing calculation. Imagine for a moment a device that doesn't just calculate faster, but calculates in an entirely new dimension. Quantum computers, already in their infancy, promise to be our first true lens into the quantum realm. Unlike classical computers that process bits of 0 or 1, quantum machines manipulate qubits, which can be in a state of 0, 1, or both simultaneously, a superposition. This isn't just a more powerful calculator, it's a fundamental shift in how we process information about reality itself. We could use these devices to simulate complex quantum systems directly, something our classical computers are hopelessly inadequate for. We might finally unravel the mystery of high-temperature superconductivity, design new materials atom by atom, or even simulate the precise conditions inside a living cell. But the most profound application could be in testing the very foundations of physics. A quantum computer could, in principle, run simulations to help us decide between the many interpretations of quantum mechanics. Does the wave function truly collapse? What happens in a quantum superposition? By creating and manipulating these states at a macroscopic scale, we might move these questions from the realm of philosophy into the domain of experimental science, offering us a glimpse into the probabilistic, fuzzy heart of existence that our classical senses are built to ignore. While quantum computers extend our reach into the microscopic fabric of the cosmos, another technology aims to redefine the interface through which we experience it: brain-computer interfaces. Companies and research institutions are pouring resources into developing high-bandwidth links between our minds and machines. The initial goals are medical, restoring mobility to the paralyzed or sight to the blind. But the long-term implications are far more revolutionary. What if you could download a new sensory modality as easily as you install a smartphone app? A BC, I could allow us to perceive the world in infrared or ultraviolet, to hear the magnetic field of the Earth as a constant symphonic hum, or to feel the ebb and flow of the stock market as a tangible force. We could share not just thoughts but raw experiences, achieving a kind of telepathy where one person's sensory reality can be directly streamed to another. This technology could finally allow us to bypass the biological constraints of our umwelt, the species-specific reality tunnel evolution gave us. We could design our own perceptual realities, merging the digital and the physical into a seamless mixed reality that is far richer than anything we can currently imagine. It would be the ultimate tool for empathy, for exploration, and for art, but it also raises profound questions about identity, privacy, and what it means to be human when your sensory input is as customizable as your desktop wallpaper. To peer into the deepest past and the largest structures of the cosmos, we will need a new generation of eyes. Advanced telescopes, both on the ground and in space, are already being designed to push the boundaries of what we can see. The James Webb Space Telescope is just the beginning. Future observatories will directly image Earth like exoplanets, analyzing their atmospheres for biosignatures, the chemical fingerprints of life. But beyond that, projects like the Laser Interferometer Space Antenna will open an entirely new window on the universe, the detection of low-frequency gravitational waves. These ripples in space-time, caused by the slow cosmic dance of supermassive black holes, will allow us to hear the universe. We will be able to test general relativity in extreme environments and witness the birth of black hole binaries that are completely invisible to electromagnetic telescopes. Even more speculatively, futuristic neutrino observatories could one day allow us to see directly into the core of stars or peer back to the very first second after the Big Bang, a time before light could freely travel. Each new telescope is not just a bigger mirror, it's a new sense organ for humanity, granting us access to a deeper layer of cosmic reality that has been there all along, waiting for us to develop the tools to perceive it. The ultimate convergence of these technologies might lead us to the most profound exploration of all, the nature of consciousness itself. By using quantum computers to simulate neural networks of unprecedented complexity, and by using brain-computer interfaces to precisely measure and interact with the brain's activity, we could finally develop a scientific theory of how subjective experience arises from physical processes. We could test hypotheses like integrated information theory by creating and measuring phi in synthetic systems. We could explore altered states of consciousness, meditative, psychedelic, or otherwise, with perfect clarity, understanding exactly which neural patterns correlate with feelings of awe, ego dissolution, or transcendence. This isn't just about understanding the brain, it's about understanding how the brain constructs reality. By reverse engineering our own perception, we may finally be able to answer the ancient question of whether consciousness is a passive receiver of reality or an active participant in its creation. The future of reality exploration isn't just about looking outward at the stars or inward at atoms. It's about unraveling the mysterious loop that connects the observer to the observed, and in doing so, perhaps discovering that the greatest frontier is the one we've been carrying inside our skulls all along. From the ancient cave of Plato to the shimmering pixels of the holographic principle, from the predictable clockwork of Newton to the probabilistic dance of the quantum realm, our journey has taken us through a breathtaking landscape of ideas about the nature of reality. We've seen how our brains construct a useful but limited interface with the world, how cutting-edge physics suggests the universe might be a cosmic computation, and how cultures and even other species inhabit realities vastly different from our own. This isn't just an academic exercise, it's a profound exploration that challenges the very ground beneath our feet and the thoughts inside our heads. The most stunning revelation from all of this is that the question "what is reality?" may not have a single, definitive answer. Instead, it might have a spectrum of answers, each valid within its own context and framework. The solid, objective world of scientific materialism is a powerful and useful reality. The interconnected, spiritual world of the animist is a deeply meaningful reality. The probabilistic, information-based world of the quantum physicist is a mathematically precise reality. These are not necessarily conflicting truths. They may be different levels of description, different ways of interpreting the same underlying mystery, each offering a unique window into the magnificent complexity of existence. A single event like a supernova can be described as a nuclear chain reaction, a tragic death of a star, a release of heavy elements that will one day form planets, or a cosmic spectacle of immense beauty. Which description is the real one? They all are. The universe reveals different facets of itself depending on the questions we ask and the tools we use to look. This understanding invites a powerful intellectual humility. It asks us to hold our own assumptions lightly and to approach the world with a sense of wonder and curiosity rather than certainty. The journey doesn't end when the video does, it begins. What does this mean for you right now? It's an invitation to become more aware of the filters through which you perceive your own life. Notice the stories your mind is telling you about what is real and what is important. Question the categories you take for granted. The next time you feel absolute certainty about something, pause and consider how your biology, your culture, and your personal history have shaped that conviction. This isn't about doubting everything into paralysis, but about opening yourself to a richer, more nuanced, and more fascinating engagement with the world and with others who see it differently. So we leave you with this challenge. Don't just accept the reality you've been given. Explore its edges, wonder at its mysteries, read about a scientific concept that bends your mind, learn about a culture whose worldview differs from your own, or simply sit in quiet observation and notice how your own mind constructs your experience moment to moment. This is the greatest adventure there is, the exploration of consciousness itself. We would love to hear where this journey has taken you. What concept from our exploration resonated most deeply? What is your own personal perspective on the nature of reality? Share your thoughts, your questions, and your own mind-expanding ideas in the comments below. Let's continue this conversation together, because the search for what is real is a quest we are all on, and every perspective adds another piece